Okay, in this video, I'm going to work through a problem in which we're going to determine if the reaction shown below is spontaneous. We're going to look at it from the delta S of the universe to determine spontaneity, and we are going to determine the delta G, the Gibbs free energy, to also determine spontaneity. So there's 4 different sort of parts of this that I'll walk you through. First, I want us to just consider, is the delta S entropy positive or negative for this particular reaction shown below there? So we have propane gas is combusted. This is a combustion reaction. So it's combusted, burned in oxygen to yield carbon dioxide and water vapor. And we wanted to figure out, is the delta S for this reaction positive, entropy or disorder increases, or negative, entropy or disorder decreases? So if we look and see what we have in our reactants, we have 1 mole of gas coming from the propane and 5 moles of gas coming from the oxygen. So we have 6 moles of gas in total. And let's compare that to what we have over here in the products. We have 3 moles of gas and 4 moles of liquid. So thinking about it in terms of disorder, I'm looking at it in terms of a reaction diagram. Our entropy for the reactants is higher than our entropy of the products. Liquids are more ordered than gases. Remember, more ordered means less disorder. Those liquid molecules aren't moving around as quickly. There's not as many collisions. It's less chaotic is a way to think about that. So the products are more ordered than the reactants. When the products are more ordered, less entropy, the delta S for this process should be negative. So that was just a reminder on entropy and thinking through entropy. Now, determine the value of the delta S and the delta H for this reaction using the following values. So this was gotten from the appendix of our textbook, and I want you to make sure you check your units. We want to determine what is the delta S and what is the delta H for this process. And this goes back to some first semester stuff as well, where the delta H of the reaction is equal to the sum of the delta H of formation of products minus the sum of the delta H of formation of reactants. So let's start with the delta H. So the delta H of the reaction, the delta H of the system, the delta H is going to be equal to, we have 3 carbon dioxides, so we're going to take 3 times negative 393.5 plus we have 4 water liquids, 4 times negative 285.5, negative 285.8, I'm sorry. That's our products, minus, we have 1 C3H8, negative 105, plus 5 oxygens. Oxygen, since it's an elemental state, is 0. So the delta H for this process, for this reaction, is equal to negative 2,218.7 kilojoules. Okay? We can do the exact same process to figure out the delta S for this reaction. The delta S for this reaction is equal to products minus reactants. So again, same process. We're going to take 3 carbon dioxides, 213.7, plus 4 waters, 69.9, products minus 1 C3H8, plus 5 205.0s. So the sum of products minus reactants. That gives us a delta S for this reaction of negative 374.2 joules per Kelvin. Joules per Kelvin. All right. So that's how we figured out delta H and delta S. Again, remember, we're trying to figure out, is this reaction spontaneous or not? And we're going to use the delta S of the universe. So is this reaction spontaneous based on the delta S of the universe? The delta S of the universe equals the delta S of the reaction plus the delta S of the surroundings. System plus surroundings. So then, let's figure out the delta S of the reaction. We already figured that out in the last slide. That was negative, where'd it go? 374.2. Negative 374.2 joules per Kelvin. We need to get at the delta S of the surroundings. The delta S of the surroundings equals the opposite of the delta H of the reaction divided by temperature. So that means it's the opposite of negative, this is the number we got on the previous slide, 2,218.7. I'm going to be really, really careful here. This is in terms of kilojoules. Divided by the temperature, I gave you a temperature of 31 degrees Celsius. So 31 plus 273.15 gives us a temperature in Kelvin of 304. That gives us the delta S of the surroundings of being 7.298 kilojoules per Kelvin. Watch your units. Units on delta S usually are in terms of joules per Kelvin, so we have to convert this. For every 1 kilojoule, there's 1,000 joules. 7,298 joules per Kelvin is the delta S of the surroundings. Now, I just want to take a step back and say that's gigantic. That much change in entropy is huge. And the reason that that change of entropy is so big is because the reaction is so exothermic. So like I said, this is the combustion of propane. This is what a lot of us use to heat our houses. We know that that reaction is highly, highly exothermic. That's because it heats the house. And so when all that heat goes into the house, you can think about it as warming up all of the gas molecules in the house, causing them to move around much, much more quickly. So heating up that much the surroundings means that the delta S for the surroundings is gigantic. So the 7,000 number is really, really big when we're talking about a change in entropy. So the delta S of the universe equals the delta S of the reaction, that's what we calculated on the last slide, plus the delta S of the surroundings, which was 7,298 joules per Kelvin. Again, keeping an eye on those units. The delta S for this process then, the delta S of the universe rather for this, is 6,924 joules per Kelvin. So is the reaction spontaneous? Absolutely. It increases the entropy of the universe. Even though the reaction itself gets more ordered because we form liquid, we increase the entropy of the surroundings so much to offset that. Finally, one more thing. I want to determine the delta G for this reaction. Is the reaction spontaneous based on the delta G? And again, we're at 31 degrees Celsius. The equation for this is delta G equals delta H minus T delta S. This is looking at spontaneity completely from the system. We don't really care about the surroundings. So the delta G for this reaction is equal to negative 2,218.7 kilojoules. That's the delta H that we determined on slide 2, minus 304 times negative 0.3742 kilojoules per Kelvin. So just again, be careful. The delta S that we calculated was negative 374. Let me write that down here. The delta S that we calculated was negative 374.2 joules per Kelvin. Watching your units, convert that into kilojoules. There's 1,000 joules in 1 kilojoule. That's how you get the negative 0.3742 kilojoules per Kelvin. So the delta G is equal to delta H minus T delta S. So the delta G for this reaction is negative 2,104 kilojoules. And this reaction is, yes, spontaneous, because delta G is negative. Negative delta G means a spontaneous reaction.